Alright, now let's continue with debugging. So let's just debug our last remove. So let's just make the tree a little simpler. So we'll just make the numbers I usually choose. So 5, 6, 11, and 13. We'll just actually just do those. Actually, we could do that, 5, 6, 11, 13, and then we will, actually, you know what, let's just do that, 5, 6, 11, and we will, so we'll take this out and we'll say heap dot remove, so remove, we can only remove the min, I believe. Yeah, so in this heap at least, or in this heap at least, you can only remove the min. You can make an element to remove the other elements if you really wanted to. In the textbook I learned from, they just remove the min. I'm not exactly sure if you are allowed to remove the other elements. If you are, you can create a way to remove them. It's pretty easy. If you have two children, you can just use the in-order successor. If you have one, you can just replace it with that node. If you have no children, then you can just set that node to null. So we will remove the min then. So 5 is a min, and then that'll get removed, and then 6 will probably become the root, and 11 will be the next child. So I think we're just gonna do one. You can figure out the whole code if you have time. This is getting to be maybe 3 hours almost, or more. So let's just go with that. Getting a firewall thing because I just changed the setting, allow IntelliJ. Okay, let's go. So we have remove min, we have our linked heap here, we have our elements there. So our linked heap is at memory location 954. We have our last node, that was 11, that's correct. Its parent should be 5. That's correct. The root is 5, its left is, oh great, these things are still in a weird order. That's okay, I guess. So we have right here. I'm not sure why it's flagged. Okay, there we go, because there's a flag. I guess I clicked a flag or something. I don't know how those work, because it's just specific to IntelliJ. So we have the root here, which is 5. The element's 5. The left is 6. The right's 11. So we're trying to remove the min, which is the 5. So we'll step in. If it's empty, throw the exception. Well, it's not empty. Just make that a bit smaller. Maybe we can make that a little bigger. That's good. So we'll step over that. So we'll say min element points to root.getElement. So t min element points to root.getElement. So t min element points to 5. So min element is a variable of type t, and then we're saying, okay, we'll point to the root, this root.getElement. So there we have min element pointing to 5 at the memory location 1009. If size is equal to 1, we're just going to remove everything, set them to null, which it's not. Then we're creating an object reference variable of type heap node. So remember, we're going to use heap node instead of binary tree node. We're going to set a heap node of type T. It's an object reference variable. It's going to point to a node. We're going to call it next last. We're going to point it to get new last node. So now we're going to probably change the last node. So it wants to change the last node. Get new last. Well, the last is currently 11. So we're going to see why they want to do that. So result points to last node. Result points to 11. While result, haven't we already been here? No, it's a little different. Okay, so well, what do we have before? Have in the add method we had get next parent add. Okay, this is get new last node. So while result is not equal to root, while result is not equal to root, that's true. And result, which is 11, dot get parent, which is 5, dot get left is null. So we're saying, okay, result, which is 11, dot get parent, which is 5, dot get left. Oh, that's wrong. Sorry. So it's result, which is 11, dot get parent, which is 5. And I have to click this here. Dot get left, which is 6. So result dot get parent. Oh, sorry, I had it right the first time. So 11 dot get parent 11. Sorry, result dot get. So let's just collapse these for a sec. So result, which is here, right? We're gonna click that, the arrow to collapse, to make it go down so we can see the list. So result dot get parent right here. Result dot get parent. They're going to say dot get left, so make sure you click that arrow and it's not those ones. So click the arrow on the side to open up its instance data. So parent dot get left, which is 6. So we're saying, well, and 6 is equal to result. Well, is 6 result? Is that memory location 1010 equal to the memory location 9? What does that say? 990? I believe that's what it's asking. And so while result is not equal to root, we got that part, that's true. And result dot get parent dot get left is equal to result. Well, that's false then. That must be false. So that was skipped. Now we're here. If result does not equal to root, that's true. Result points to casted heap node to result. Dot get parent. Dot get left. Excuse me. So result points to 6. Result. So now result's going to change to 6. There we go, a change. While result dot get right. While result dot get right does not equal to null. Well, it does. So then we're going to say return result. Result was 6, so we're asking for the get new last node. So right now we have 5, 6, 11. So that's what they want for that. I'm not exactly sure what the point of that was, because we're just trying to remove 5, put 6 in the root, and add 11. So I feel like 11 should have been the last node. But it's probably going to change still, so maybe it's just the current last node that they're going to use for some reason. Unless I made a mistake, but we'll check that it's correct. Where are we here? Okay, so we're going to return result, which is 6. So next last points to get new last node, which is 6. If last node, so if last node dot get parent, so if last node dot get parent, if last node dot get parent dot get left is equal to last node. Well, what's last node? 11. So it looks like it's not equal. That should skip. Else last node. Let's just collapse all these again. So last node, which is here. Looks like we lost our last node. Okay, so last node is here. Last node dot get parent dot set right to null. So we're going to remove the min, and in order to do that, we're gonna set the right to null apparently, because that's what they want to do. They want to move that 11 up, so they're going to say, okay, well, we're going to set that spot, that get right area, or that right child area to null, and so we can move that. So they're not actually shifting the elements up. Again, they're just setting the elements. So they're changing the numbers internally. They're not actually moving the memory locations around. Personally, I don't really like that way, but that's okay. It's an easier way. If it works, right? Doesn't really matter. But before, we were actually moving the memory locations around. That's fine. So we'll continue with that. We'll set that right. So we're going to say, okay, last node dot get. So we'll collapse that. Last node here dot get parent, which is 5. Set its right, which is 11, to null. Done. Then we're going to say, okay, well, root. So last node's right. Sorry, last node's element is still 11. It's still holding 11 even though that right was set to null. We're just setting that parents, right now we're setting that parents right to null. So that's what you have to be careful with. Sometimes if we just set the parents right to null, doesn't mean it's completely nullified. So you have to make sure that the parent and the child's nodes are nullified. So you can do that with a check at the end or a check in the beginning. I mean, in the middle, doesn't really matter. Personally, I'll just do all the nullifying at the end, but this is almost, this is the end of the method anyway, so here it's saying root. Let me just remove those watches. So here, so this root, which is 5, set the element to the last node dot get element, which is 11. Not sure why they're doing that exactly though, because we wanted the root to be 6, but it's probably going to heapify itself after, so that's okay. So here we're saying, well, last node points to next last, which is the 6. Done. Then we're going to go into heapify remove, because right now our tree looks like this. We have a root of 11. Its left is 6. Its right was set to null. Like, there's different ways to do this, right? We could have done this probably a bunch of different ways. This was one way that they wanted to do it. So we have here root is 11. Right was set to null. Left is set to 6, and it's all that stuff is set properly. So we have here root, which is 11, its parent should be null, so that's fine. Now we're going to swap them because the order is not in a heap order. We're going to go into heapify remove. We're going to say, okay, well, heap node of type T node points to heap node casted root. They're just going to say, okay, well, heap node, an object reference name heap node of type T, name node is going to point to root. That's all that it's really saying. So node points to root, which is 11, because right now our root's 11. We're going to say, well, the left is node points to node.getLeft. That's going to point to 6, so left's going to point to 6. Right's going to point to, should point to null, so node.getRight is null. That should be null. So if I collapse all that, then we have right is set to null. Maybe we should have done different names, since we already have those names. That's okay. We have roots left and right. Okay, it's fine. So then we'll say heap nodes next. That's set to null. It doesn't go to that line because anything null just gets skipped, I think. So we just have that longish set here, and we're done. So if left is equal to null and right is equal to null, well, that's false. That's gonna get skipped. I don't like how these brackets are set up because they're kind of confusing, but this is all else. If, else, if, else, if, else. So it's all one thing. It's either this, it's either that, it's either that, or it's either this. So else if right is equal to null, so that's true. They're going to say, okay, well, next points to left. So next points to left. Right here, next is equal to left, or next, I say points, so next points to left. Where's next? Next is null. Next, okay, it's currently null, so next is now going to point to left. Should see a new field pop up there, and then we'll say temp points to node dot get element. That's 11, so temp's going to point to 11. Okay, so the next block here, so while next does not equal to null, next does not equal to null, that's true, and next, I think it will go through here to heapify itself. So while next dot get element, which is 6, dot compare to temp, which is 11, is less than 0, so yeah, 6 is less than 11. That returns -1. That should enter the statements node dot set element. So node points to 11, set element to next dot get element, so it's going to swap the elements. Again, personally, I don't like setting the elements. I would have just swapped the nodes themselves, but it's totally up to you, whatever way you want to do it. When it comes down to it, you can do it whatever way you want. This is just from the Java Foundations textbook. The way we did it before is we went in our binary search tree, we actually set the lefts to the node. We went set left. We didn't use set element. That's what we used. We used set left and set right. We didn't use set elements. We just carried that. We just swapped we moved the actual memory locations around. That's what we were doing. That seems like the better way to do it. Because let's say you had not just one element here. You had like 1,000,000 elements in this node. You had 10 million elements in that node. Let's say you had 10 million user accounts stored in one node, and you wanted to move that node somewhere else. Then you would want to move it by memory location. You don't want to set the elements again. That would take forever, right? So personally, the way we did it before was better. This is just the way the book's teaching it for a heap. Again, you can probably implement it to set its left and set its right, using a temp to point to the one you want to rotate. It's technically going to be a rotation, I guess, in that case, and that would probably be a better way to do it. But do heaps only store a number? I'm not sure. I'm just googling it right now. Do heaps store numbers only? What are heaps used for? I think it's just for numbers. Doesn't really say what they're used for. So binary heap, perhaps to store binary data within the computer itself. So it might just be for numbers itself. So maybe that's why we're just setting the elements, because maybe it's just storing binary like 0 and 1s or something like that. It doesn't say it stores actually any data, like big data, so that's okay. We'll just go with it, but again, you can implement your own version of a heap if you want to change it. You could call it like a super heap or something. Whatever you want. Tree heap, whatever. So here we're going to say, okay, well, node set the element. So node, which is 11, set the element to next, which is 6, dot get element. So it's going to set the node that's probably the root to, well, just a node for now. Node dot set to 6, basically. There we go, node changes 6. They're going to say, okay, well, node points to next, which is 6. Left points to node.getLeft. It's a little, should have maybe connected 11 there, but that's okay. So then right set points to node.getRight, which is also null. If left equals to null and right is equal to null, that's true. Then next points to null. What happened there? Next. Okay, so with this we're in a loop here. Were we in a loop? I guess we were. We were just here. Next points to null. Then okay, so then after his set bracket only has these choices. So we hit this one. If it wasn't this one, so since it was this one, it wasn't this choice, wasn't that choice, and it wasn't that choice. That means it went to the bracket, looped back up. Now we're at the condition again. We're gonna check the condition first. Loops back up to actually here. Then we're gonna say, okay, while next, which is null, does not equal to null. So while next does not equal to null. Well, it does equal to null. See, look. While next does not equal null. That is null. It doesn't say while next is equal to null, right? It says while next is not equal to null. So it's not null. So it says while next is not null, so that's false. So this whole thing should get skipped. In that case, sometimes it can be a little confusing because it's just like, or just you want to double check it, right? So then it goes here now to node.setElement. So we're saying, okay, well, node.setElement to temp to 11. Mod count return min element. So now we're going to look at our heap. The root 6 and our left is 11. So it's a little confusing on that heapify add. Can we get to that last part actually, just to where we were? So I'm just going to stop that. You don't have to do that. I'm just trying to just check the root at that last point. Let's step in. Skip. Where we were like, are we here? No, we were in that heapify remove. Okay, we want to step into that one. And I want to be on that last, I want to be on here, node.setElement. There we go, node.setElement to temp, so node which is 6 times 11. Let's check the root right now. Root is 6. Left. So node here points to root. So node's pointing to the root. Then we're saying, okay, well the root, is it pointing to the, no, it probably changed here somewhere. Node points to next, okay. What's next? It's a little confusing. I mean, it's their logic. If it was your logic, you'd know what you're doing exactly, but we're following someone else's logic here. Is there no more next? Might have been set to null. So it looks like node initially pointed to root, and somewhere around here we changed it. Node points in next. Then if left is equals null and right is equals null, I think we did get to there, and the next was set to null. So that means node is that pointing to the root? Nope. It looks like it was pointing to the root before the 11 was moved around. So that's the problem with this heap implementation, when you can't refer to the original memory locations because we've shifted the numbers around themselves. But here we're just saying, okay, well, node's pointing to a node that we changed. And we're going to say, I think it's pointing to the root's left child. Then we're going to say, okay, we'll set the root's left child to 11, because that's what temp is. That's probably what it's saying. There. Root's left child. Yeah, see, there you go. Because I think right before that, let me just do it one more time just to just explain something. So we'll step in there, skip that, skip. Step in, skip all that. Skip. See, there we go. Next points to null. It was originally pointing to 6. Is that the root? I don't think that's the root because the root was swapped. That gets set to null. Then we're here. Okay, so here, look at this. Root is, where is this? This root. Right there. Its left is 6, right? So then we're gonna execute this line. His left was changed to 11, so that was the purpose of it. The steps in this, it's a little confusing. Again, if you were to write it yourself, you'd have more logic. You could do it a different way. You could definitely do it a different way. You could just set the memory locations. You don't need to rotate the numbers and all that. So this is just one way to do it. So this concludes the This concludes the tutorial on heaps. I think we did everything. We did add element, remove element, and find min. So yeah, so I hope you understand, and if this video helped you in any way, if you want to see more free educational content and on coding videos, or any free educational content on investing or trading, or algorithmic trading, trading bots or anything, you can subscribe to the channel if you'd like, and I'll see you guys in the next video. Take care.